Hello everyone, good evening. This is the tutorial on PCA. We are waiting for the speakers to join. Thank you. Hello, Professor Tangirala. This is Devasattam.
Yes. Good evening. Sorry to keep you anxious.
No problem. No problem.
Are you able to see my video clearly?
Yes, yeah.
Okay. Thanks.
Hello everyone. Welcome again. Good evening. We'll start in a couple of minutes. Is that okay, Professor Tangirala?
Yeah, absolutely fine.
Okay. Professor Narasimhan would be joining us this evening.
Yeah, he should be. Maybe I'll just call him and check. He should be.
Great. I can also call him up.
Yeah, please.
Okay, I'll call him up. Yeah. Okay.
Hi, Sanjay. So I hope you got our email.
Yeah. I'm sorry, I was in session, so couldn't reply. But
No,
yeah,
no.
that's perfectly fine.
Yeah, I tried calling Professor Narasimhan, but he didn't pick up the call.
Let me call him on a different number. Just give me a minute. I'll call him.
Sure, sure.
Okay, so I just managed to speak to him. He said he'll join in 5 minutes, but we'll get started.
All right. Sure. So welcome everyone. This would be fourth in the series of tutorial sessions on the topic of principal component analysis and their new variants. We are pleased to have Professor Arun Tangirala and Professor Shankar Narasimhan from IIT Madras, Department of Chemical Engineering, who are giving this series of tutorials. So without further delay, I leave the podium to Professor Tangirala.
Sure. Yeah. Thank you, Dr. Devasatham. Yes, so this is part 4 of the series of tutorials that we have been giving since yesterday morning. And for those of you who have been following since yesterday's talks, you can see the title slowly growing bigger. So we started off with the linear regression. That was the shortest title you could think of. And then in the evening yesterday, I spoke on linear steady state identification using PCA. And this morning, I spoke of linear steady state identification using iterative PCA. And now it has grown into linear dynamical model identification using dynamic IPCA. So obviously, this is not a coincidence. It has been planned that way. You start with the vanilla PCA, which is what we talked about yesterday, and a simpler problem, which is that of steady state identification. And then this morning, we studied iterative PCA to handle heteroscedastic errors, that is errors with unequal variances. And those two, so yesterday's talk and this morning's talk, they set the tone for the talk now, which is on identification of dynamic models. And since it's a dynamical system that we are going to look at, you will need a dynamic version of the iterative PCA to handle the situation. Okay, so just to give you a quick recap and help you put things in context, we are studying errors in variables identification. And the way you recognize that you're looking at EIV ID is to see that we have sensors on both input and output channels. Whereas in classical identification, you would have sensors only on the output channel. And that's important to know. So again, putting things in perspective since yesterday, we started with steady state. Where we said we need to identify the constraint matrix A. And then for the homoscedastic case, we said we just need to identify the error variance that is common to all channels. And this is where we used PCA. And from here, we went to, again, steady state identification. But this time we said the error variances may be unequal, and this is where we turned to iterative PCA. And now we are moving to dynamic identification, where we have to estimate the constraint matrix A and a bunch of other things that we will see shortly, namely the process orders NA, NB, delay, and then of course sigma E. So today we will, in this talk, we'll focus on DIPCA, which is dynamic iterative PCA. And the ideas, the concepts underlying all these methods are essentially coming from linear regression. That is what we had yesterday morning, where we looked at OLS, WLS, and then TLS and WTLS. Okay, so these are the ones that that feed to all the three cases. Of course, there is a PCA, which is very important, and you can add, for example, here the most important thing, which is SV. And when we transited from steady state homoscedastic case to steady state heteroscedastic case, we also noticed that an additional criterion has to be satisfied, which is that of identifiability criterion, which essentially says there has to be sufficient redundancy in your data to be able to identify both A and sigma E. Whereas with the homoscedastic case, it is just about redundancy. Even if you have one constraint, you should be able to identify the constraint matrix A and get sigma square E. But as we saw in the flow mixing example this morning, just having one constraint among a bunch of variables is not going to help us. Sorry about that. Having one constraint among many variables is not going to help us, because we need to estimate sigma E as well. Of course, if you know sigma E, then that identifiability criterion goes away, and the extra redundancy that is required in IPCA goes away. Now, as we transit from steady state to dynamic identification, we will see that we will need some more redundancy, because we need to estimate NA, NB, that is the input order, output order, delay, in addition to A and sigma E. Okay, so just give me a minute. Sorry about that. So we will see what is the additional thing that is required. And fortunately for us, as the number of parameters that or the unknowns that have to be estimated increases as we go from steady state to dynamic identification, the good news is that we have more information in the data, because now you have transients. That's a big plus point that we have, and we are going to explore that. And of course, there are going to be a bit of challenges, and how do we tackle that challenge is what dynamic IPCA is all about. Okay, so here is the problem statement, and we will restrict ourselves to single input, single output systems. All right. So the objective is to identify the standard difference equation model. There is nothing complicated about this model, a very basic model that we learn to identify in the 101 of identification, or basic model that you encounter in linear systems theory. The objective is to estimate or identify NA, that is the process output order, NB, the input memory or input order, delay, and delay of course is going to be less than or equal to NB, and the parameters AIs and BJs. So These are the ones that have to be estimated. And in addition, we will also have to estimate variances of the output and input error. So it seems like a lot of unknowns are being estimated from the data. But it turns out beautifully that there is so much juice in the data that if you do a good and systematic job of it, it is possible to estimate these many unknowns. And in fact, you can go one more step ahead as I'm not going to discuss it here. We are also able to tell you with the help of PCA, which is input and which is output, which means that we will be able to solve the causality problem. And that is something that we have recently not published, but it is a manuscript that is under review. So what I'm trying to do is, in addition to estimating these many unknowns, even if you don't tell me which is input, which is output, I'll be able to tell you that as well. So that's the beauty of a systematic extraction of information from data. And needless to say, we will use the PCA approach for solving this EIV identification problem. Okay. So what are the assumptions that we are making? We are assuming that the deterministic process is linear time invariant, and we'll confine ourselves to single input, single output systems. And we'll also assume that errors are stationary and Gaussian distributed. And also let me add stationary, white. If I say white, that should take care of the stationary part. And Gaussian distributed. And we'll assume that sigma E is diagonal. You can refer to the morning talk as to why we assume sigma E to be diagonal. As far as existing literature on EIV identification is concerned, we are not talking of classical ID. No method that simultaneously estimates orders, coefficients, and noise covariances exists. There are a few methods that assume, for example, noise covariance matrix to be available, and then you can estimate the orders and coefficients. There are a few methods that assume order is known, and then they estimate the coefficients and noise covariances and so on. So it is basically one of these is assumed to be known, while the other two are estimated. And typically, order determination is done through the use of information theoretic criteria. Now, order determination is a problem that is unique to dynamic model identification. It's not in steady state. This issue doesn't arise at all unless you say that I do not know how many constraints are there. Then it amounts to order determination. But here, I know the number of constraints. I know that there is only one constraint relating input to output. So the problem is now that of order determination. So you see people using AIC or BIC or cross-validation or some other minimal resonance MDL method and so on. But those are still considered heuristics. Here, we are not going to use any such heuristics and estimate the order accurately. And as I said, there are methods that can estimate model coefficients for known order if errors are homoscedastic. So pretty restrictive for that matter. And the heteroscedastic case was attempted in a work by Vijay Sai Gudi and Lakshmi Narayanan in 2005, but they assume that sigma E is available, which we are not going to assume. We are going to estimate sigma E as well. Okay, so let's move on and see how we recast this problem. And here is the key. I think the next two slides are going to tell you how we convert or we recast this problem so that it is amenable to PCA. And part of what we are doing is not new, I must say, but there is something very novel that actually cracks the main problem in hand, which is that of order determination. So the first perspective to remember, as I mentioned yesterday, every model equation is also constrained. Of course, this is something that we have talked about, but this is something that is very rarely talked about. Although everybody knows about it, but it has not been exploited in such a way that PCA can be used. This is a repetition of what I said yesterday. So every model is a constraint, but with partitioned variables, right? So the difference between constraint and a model is that in constraint, there is no distinction between independent and so-called dependent variables, whereas in a model, there is a prior partitioning that is done. So we will ignore that those labels on the variables as we did in yesterday's and today's talk, and club all the inputs and the outputs. And now, since we are looking at a dynamical system, we have to include past outputs and past inputs, because the model itself says that there is a relation between all of those. Now here we introduce a quantity called process order eta. So we call this as a process order. It is the max of the input and the output order. So we because we do not know NA and NB, that's the point. So let us assume that there is an eta, which is a max of both. And how do we choose eta is something that we'll talk about very soon. How do we calculate eta? How do we guess and so on? So for a specified eta, we stack Zn star as in equation 4. And the original equation that we wrote earlier, which is in equation 1 here, now can be rewritten in terms of eta. Obviously, since eta is max of Na and Nb, in the new model formulation, some of the coefficients will be 0, right? I think that goes without saying. So you can see the number of zeros will depend on whether Na or Nb is the one that is governing eta. And of course, D is also unknown. The delays are also unknown, and we have included that as well in our constraint. So this is a full-fledged model involving some non-zero values in the constraint. Yes, it is a single row, but we still prefer to use a matrix for reasons that will be clear very soon. So it's a full-fledged model where the constraint has non-zero elements and zero elements, and there is a certain structure to it. In one of our early papers, we have exploited this structure to identify, but later on, we kind of kept the structure aside and used a more powerful method to identify these unknowns. Okay, so the first step is to rewrite the model in terms of a constraint involving this process order. So the problem of identifying the difference equation originally, that is in equation 1, is all about now determining the process order eta and the constraint matrix A eta. Of course, when we do that, in place of the non-zero values, we will end up with some, in place of the zero values, when we identify A hat will not have these zeros necessarily. Okay, there will be some non-zero values, because you're going to only obtain a basis. And how do we resolve that? Well, you first write this constraint form in a regression form, and then you can do bootstrapping to determine which of the regression coefficients are insignificant, and then eliminate those so that you work only with the non-zero terms in the model. That's the idea. So the message that we have is that if I have a constraint for a dynamical system, they can be viewed as a steady state model in terms of lag. So we have converted a dynamical model to a steady state model in terms of lag variables, right? Usually in control and other systems theoretic applications, this is realized through transform, for example, Laplace transforms, Z transforms, and so on, where you go from a dynamical model, like a differential or a difference equation, to an algebraic model through Laplace or Z transforms. Here we are not using any such transforms. We are still living in the time domain, and all we have done is we have introduced lag variables, and we said, let us view this dynamical model as a steady state model in terms of lag variables. So for a given eta, the identification of the dynamical constraint in equation 2 is all about identifying a static linear relation between lag variables. So we have now boiled it down to the problem that we have already solved in yesterday's and this morning's talk. The difference between yesterday evening talk 2 and talk 3 is the homoscedastic versus heteroscedastic. But in both cases, we have talked of steady state identification. And now hopefully it is clear why we have progressively arrange the talks in this fashion. So natural method for identifying linear relations among variables, the EIV case is the PCA. So just to quickly recap what we have learned in talk 2 and 3 is that given a bunch of constraints, so suppose Z star K are instantaneously related through D linear relations or constraints, then the standard PCA provides consistent estimates of both D and A when the errors are homoscedastic, and iterative PCA is able to offer the same solution for the heteroscedastic errors. So homoscedastic, you can use PCA, and for the heteroscedastic case, you can use iterative PCA. And in both cases, the model, the constraints as well as the noise variances are identified. And the key idea in IPCA, just to emphasize, and for those of you who missed out on the talk in the morning, is to scale the data with sigma E to the -12 and implement the standard PCA. And the sigma E being unknown has to be estimated iteratively. And that's why the name iterative PCA. You guess a sigma E from an initial PCA implementation. And then you scale the data and you iteratively estimate the constraint matrix and sigma E until convergence. And as I said at the beginning, there is an identifiability constraint that governs IPCA, which says that there has to be sufficient redundancy. D essentially denotes redundancy. So D into D plus 1 by 2 has to be greater than the number of unknowns in sigma E. And if you have a diagonal sigma E, then the number of unknowns is simply the number of columns in A. For steady state, the number of columns in A is the same as the number of variables. But for the dynamic case, the story is different. Why is that? So let me take you back. And this is something that I want to see it up front. Now, the dimension of A, or the column, number of columns of A is different. You can see how many columns are there in A. You have 2 eta plus 1. So A eta is 1 by, look at it here, 1 by 2 eta plus 1. That's the number of, so yeah, 1 by, yeah, you'll have, 2 into eta plus 1 by 2 into eta. Now it's no longer M variables. We have only 2 variables, so to speak, one input and one output. But as I mentioned even yesterday, the size of A now changes because we are including lagged variables. Okay, so that is something to keep in mind, which means that we will have to keep that in mind at the identifiability constraint. But having said that, in the dynamic case, sigma E, which is generally of dimension M by M, here, since there is only one input and one output, strictly speaking, there are only 2 unknowns in sigma E if you assume diagonal sigma E. So that is to be remembered. We will, I will again point that out later on. So how have people handled dynamical models using PCA? We are not the first ones to do this. Nearly 25 years ago, there is this very famous paper by Koo, Storer, and Georgiakis, who proposed dynamic PCA. And the idea was the same thing that I've discussed. Perform PCA on a matrix of lagged variables. But they assume that the orders and delay are known a priori, number one. And that's a big piece of information. Typically, you'll have to really know that. And secondly, this DPCA suffers from the same restriction as that of PCA, which means that the error variances should be identical in both input and output channels. So just to illustrate this point, let's consider a unit delay second order deterministic seesaw system. The equation is given, the model is given in equation 7. And let us assume that the orders and delay are known. So that means I stack exactly based on this model. All I all I do not know, all that I do not know is the coefficients and sigma squaring. So I stack in this fashion, and this is our Z. And because there is a delay of 1, our stacking begins from 2. We could observe that. We do lose out on 1 observation there. Okay, so that is standard. Even in classical identification, you see that. Now, what we did was we generated about 1023 observations. We used a full band pseudo random binary sequence. For those of you who do not know what a PRBS is, it's essentially a binary sequence that switches between plus and minus 1 in a random fashion. And a full band PRBS essentially has white noise like properties. So it has all frequencies present. It contains very narrow pulses to wide pulses. And it's pseudo because it's not truly random. You can generate it by yourself. But it is random because it has a random signal like properties. Okay, so we also looked at 2 scenarios. We simulated the system under homoscedastic errors and heteroscedastic errors. The values of the noise variances are given. And we did Monte Carlo simulations to determine the averages of the estimates that we obtain from DPCA. So what is the idea? Once you have this Z, you apply PCA on this because there is only one constraint among the relations, and because it's a if it is a homoscedastic case, you will see, you will essentially apply what is known as the last principal component analysis. You know there is only one constraint. So you look at the eigenvector corresponding to the last eigenvalue and get the coefficients. But for the heteroscedastic case, if you try to do the same thing, you will run into problem like we saw this morning. So the parameter values are given here, the true ones, and these are the mean values obtained from MC simulation, very close to the true values. The standard deviations are indicating that the estimates are all significant. But if you look at the heteroscedastic case, as expected, based on what we discussed this morning, you see bias in the estimates, right? This is not surprising. Okay, so even when the orders are known, we have a problem, and the delay is known, we have a problem here. And this problem is not new to us, considering what we discussed in the morning. Now, let us now become a bit more realistic and ask what happens to DPCA if I do not know the order and delay. Because this is a stepping stone for DIPCA, our method. Now it turns out that if you do not know the order, what is the thing that you can do? You'll have to guess the order. And you don't necessarily guess separate orders for output and input. That's not a wise thing to do. You simply assume some order L, which is hopefully greater than the true order, right? You obviously don't want it to be lesser than the true one, then you will not have any constraint at all among the columns of Z. So you assume some value of L, let's say 4, 5, or 6 or whatever, and then you estimate the coefficients. And hopefully using bootstrapping or some other method, you will be able to eliminate the insignificant coefficients. So in this case, we chose L equals 3. That's our guess. And because you choose L equals 3, Z would have 2 into 3 plus 1. That's 8. And that's why there are 8 columns in Z. And because we have assumed L equals 3, you will have to actually sacrifice the first 3 observations. So you have only 1020 observations. And the eigenvalues are obtained here, reported here. Okay. Now, what do you notice? It's still the homoscedastic case. So what are you searching for? You're searching for equal eigenvalues and small equal eigenvalues. And if you talk of small equal eigenvalues, you will pay attention to these. So which means that now our PCA is telling us that there are 2 constraints. Now, that's a bit surprising, isn't it? Because we said it's a seesaw system, there has to be only one constraint. So is this meaningful? And the answer is yes, it is meaningful, Because we have overstacked, we have exceeded the true order. What should have been the choices that we should have made? If you go back, we should have actually chosen L equals 2 at the max. I mean, minimum, of course, but that is the one that we should have chosen. Now that we have chosen L equals 3, what happens is as follows. Let me probably write this on a. So you have now Z as YK. So you have ZK as YK minus 1, YK minus 2, and you have YK minus 3 because L equals 3. And you also have UK minus 1, and then want of space, I'll write it here, UK minus 3. What happens is when you stack all the observations, there is one relation that is tying YK minus 1, YK minus 2, and UK minus 1. So this is one relation. Then we have a second relation that is tying, you can say YK minus 1, YK minus 2, YK minus 3, and UK minus 2. Right? So because of the excess stacking, we have actually two constraints that are appearing. Of course, we know because it's a dynamical system, they are actually constraints that are shifted. But the fact is, PCA doesn't know. PCA says, you didn't tell me that these are actually lagged variables. I am treating each column as a separate variable, and I see two linear relations between the columns that you have given me, and therefore it says yes. So there are, so essentially, if you ask PCA, it says there are two linear relations. Now, what would be the answer, or what would be the number of linear relations if you had set L equals 5, right? Or let's say L equals 4. L equals 4 would have given you 3. L equals 5 would have given you 4 linear relations, and so on. And that is the one that we exploit. So we know that there is a relation between the number of constraints that are identified and the stacking lag and the process order. So in this case, you can see eta equals 2 by our definition and L equals 3. If I had chosen L equals eta, what I have observed is there are two constraints, D equals 2. If I had chosen L equals eta, which is 2 in this case, then I would have obtained D equals 1. Exactly. If I choose L equals 4, I would have obtained 3 constraints and so on. So which means that clearly there is a relationship between the process order, the stacking lag, and the number of constraints that you identify. And this is, I think, the key. This is one of the, I would say, the main results that allows us to go past the order barrier. And what is the relation now? You can say D equals L minus eta plus 1. So that when L equals eta, you would have stacked it accordingly. It will be only one constraint. Now, when you do PCA on your stack data, you know D, you know L, right? Therefore, you can rewrite this as an expression for eta and derive this. Okay. So that's the main point here. So hopefully, I mean, this is a fairly simple logic that is involved. There is no rigorous mathematical proof that is required on it. Any questions at this point regarding what I have written? Okay, so if there are no questions, I'll proceed. Now the question is, yes, so we have realized that there are repeated constraints that are going to occur because I have stacked in excess. And why did I stack in excess? Because I didn't know the order. Can we recover the single constraint now? Any guesses? Anybody who wants to answer this? So can we recover the single constraint from the two identified constraints?
So they should be linearly dependent or something.
Which ones?
The two that you identify?
They are not linearly, they're shifted in time. So there is a certain structure that you can get. But the difficulty is that the constraint matrix that you identify is not going to have the theoretical structure. You are going to identify only a basis for it. So you can rotate it in such a way that you get the structure. That is the first method that we devised. But later on, we realized that such a rotation is not required, and there is a simpler way of dealing with it. And the answer lies in what I derived just now. So I derived an expression for eta. So now you have the gold mine, which is eta. So if I give you eta, how will you go and identify the single constraint? When we started off, we didn't know eta.
You just read off those elements of that.
No, you can't do that because they are all bases. They are all,
Oh, yeah.
yeah. So what you do is you're almost there. You restack. So all you do is you go back and say, I'm going to reconfigure my data matrix with L equals eta.
So you run PC again on the
That's
restack.
it. Absolutely. That's all. Because that was the issue, right? With the dynamic PCA, that the order was unknown. And whenever the order is unknown, you stack in excess, you get multiple constraints. In fact, there is no discussion on that in the literature at all. After DPCA, hardly anybody talked about it. They assumed that the order is known. But the reality is that you will not know the order. You have to stack in excess. You'll run into multiple constraints. And then you can do either a rotation of the constraint matrix, but that's a kind of a complicated method. The best is to just get the eta and reconfigure it and redo it. Of course, you apply IPCA to handle the heteroscedastic case. That's all to it. DIPCA is all, the major barrier is getting the process order. No AIC, no BIC, nothing. So now we are at DIPCA. So what do? We guess L, eta as L, and you set up the data matrix and then apply a two-step IPCA. You identify the process order and estimate sigma E for a chosen L, right? You apply IPCA in both cases. That is, in both the steps, you apply IPCA. You don't apply PCA because you do not know a priori whether it's a homoscedastic or a heteroscedastic case. So now that you have eta and sigma E from step 1, you go and reconfigure with L equals eta and then scale the matrix with sigma E to minus half and apply PCA. That's one go. You don't have to actually do any more iteration. The second step is not iterative. Only the first step involves iterative PCA. Second one is also iterative, but since you know sigma E, you will simply scale and apply PCA on the scaled reconfigured data matrix to get your A. So now some practical challenges. Of course, I've already talked about the big challenge, stacking with L greater than eta, repeated constraints. I've already given that. And remember that even if you know the process order, you will still have to stack in excess because you need the redundancy to estimate sigma E. This is exactly what we said in the morning in the IPCA. The identifiability constraint has to be satisfied. Even if you know the number of constraints, you will still have to ask if it satisfies identifiability constraint. But the difference between steady state and dynamic cases, in the steady state case, if the constraints are such that the identifiability criterion for estimating both A and sigma E are not met, you cannot do anything. Whereas here, in the dynamic case, you have that opportunity because there is more information. You are using the lagged variables, and that's what I said at the beginning of today's talk, that essentially, as you transit from steady state to dynamical systems, there is this additional challenge of estimating the process order, but now we have crossed that barrier. And we also cross another barrier now, which is that of identifiability criterion. You can stack in excess and overcome this identifiability criterion issue. Okay, so what is the minimal recommended value of L? The minimal is 2. That means you're assuming at least a first order dynamical system. So you will have to stack at least with L equals 2. Typically, we recommend that you start with L equals 10 or 15. I'll show you that stacking in excess does not have too much of an impact on your estimates. You can do L equals 15, 20, and so on. So for those of you who are familiar with subspace identification methods, this sounds pretty familiar. But in the end, in the subspace identification where you have to figure out the rank of the extended observability matrix, there is a heuristic. And this particular comment of mine is very, very relevant because in tomorrow's talk, when Shankar talks about state space identification using these ideas, we overcome that barrier also, where you don't have to now turn to heuristics for determining the rank of the noise-free extended observability matrix. We can see through the noise and get it done. So in one way, the order determination problem has been kind of solved in such an elegant way. So this is the DIPCA methodology. You construct the data matrix ZL by choosing a sufficiently large stacking order. And depending on what your guess of the order is for the system, you will have to choose L more than that. Minimum is eta guess plus 1. And as I said earlier, although sigma E is of size 2 into L plus 1, there are only 2 unknowns. So that modification also has to be made in IPCA, but that's a very minor coding modification. And then once you run your IPCA, this will give you sigma E hat and D, the number of constraints on the ZL. And from there, you recover eta, you reconfigure your data matrix using L equals eta hat, scale, and that's it. So you finally obtain the difference equation. That's all through the IPCA and the DIPCA. So a couple of case studies and I'll close my talk. So the first case study is a very simple one. Both case studies are there in our original paper on DIPCA. So the NA is 2 here and NB is 1, delay is 1. And once again, we use a full length or a white noise like PRBS. You can use a band limited PRBS also, as long as the excitation requirements are satisfied and your excitation is within the bandwidth of the system, there should be no issues. And we once again set SNR to 10, add noise in such a way that SNR is 10, and just a snapshot of the input and output noisy and noise-free measurements. Sorry, you may not be able to see clearly unless I zoom in. So this is the input measurement and this is the output measurement. Okay, now we choose L equals 5 for the system, and as expected, so the theoretically you should expect 4 constraints because you have eta equals 2 for the given system, right? Okay. Eta is max of NA and B, so eta is 2. Therefore, you should expect D is 4, and that is how we get it. Now, I did talk about the choice, the guess that you have to make in IPCA. And I mentioned this morning what happens if you guess lower than the true value and guess larger than the true value. The true value is 4 here. We start with a D guess as 2, and we ask how many unity eigenvalues we get. So we say there are 2 unity eigenvalues. Yes, I'm eyeballing here, but there is also a hypothesis test that you can conduct, and that is reported in another paper. And it's also available as a part of the GUI that we have developed, or the toolbox that we have developed. So even eyeballing, you can say that there are 2 unity eigenvalues. So we proceed because we will, when you start from a lowest value or low value of D, the rule is that you increase until this condition breaks down. So you go to 3 constraints and you get 3 unity eigenvalues. 4, you get 4 unity eigenvalues. The moment you cross the real barrier, you see the unity eigenvalue is broken down. So by the way, I'm plotting log of lambda here. So our reference line is a 0 line. So you can see the moment I cross the true one, the matching between the guessed number of unity eigenvalues and the realized unity eigenvalues is broken down. So we settle with D hat equals 4. As I said in the morning, you could start with a high value of D and decrease until you meet the requirement the first time. So with this, we get eta as 2, which matches with the true order. And then the rest of the procedure, as you know, we reconfigure the matrix and run and scale the data and run PCA on it. Obviously, since we have taken, we have stacked both Y and U up to 2, you will have And since we do not know the delay, you will have certain insignificant coefficients. So these are the two insignificant coefficients. How do I know that's insignificant? For the purpose of the study, we did Monte Carlo simulations, but we have now a bootstrapping method that's a part of the GUI, and that doesn't require any MC simulation. From a single data set, we'll be able to tell you whether the coefficient, the estimates are significant or otherwise. So you can see from the 95% confidence interval that 0 is contained in the estimate of B0, confidence interval for B0 and the confidence interval for B2. So we failed to reject the null hypothesis for B0 and B2, whereas for A1, A2 and B1, the null hypothesis is rejected. So that's it. So that's as far as the estimation is concerned. We also observed that the estimates are consistent. So we did Monte Carlo simulations for different sample sizes and setting the signal to noise ratio as 4. And you can see the width of the confidence intervals shrinking as the sample size increases. So we go from 5, we double, and then we almost make this 8-fold. And you can see that the confidence intervals are shrinking, right? Okay, so that kind of at least gives hope for consistency. We don't have a formal proof for the consistency of DIPCA, right? Shankar, I think we have not yet derived a formal proof.
No, we are not. I mean, I don't know whether we'll be capable of, we need some mathematician to look at this. I've been looking for somebody to help us.
Yeah. So if there is a mathematician here listening to us, they can come forward. Okay, so let me also show you the effect of stacking lag L. So just reporting the estimates that we obtain for A1 hat, B1, B0 hat, and sigma square y for different stacking orders. On the x-axis, we have different stacking orders. You can see that essentially, as you increase L, yes, you lose out on the sample size because you have to sacrifice few data points, the redundancy increases. But so the loss of sample size is compensated some way in some way for with the increase in redundancy. But I must say that here the L that we have chosen, the max L, is still much less than N. Of course, if you choose stacking orders L very close to N, you will get obviously terrible results, but you should not be doing that because that's a terrible choice for L. Remember, L has a meaning. L, by specifying a value of lag L, you are saying that implicitly, this is my guess of the order of the process. So if you're choosing a very large lag value for L, you are indicating that that the process order is very, very high, right? An L of 1000 would be atrocious. Yeah, that means you're saying that the process is 999th order, and maybe for all practical purposes, it's a nonlinear system. So you don't want to get into that. So practically speaking, the effect of stacking lag L, as long as it is much less than N, doesn't is minimal or negligible. So just to compare again with the DPCA for the homoscedastic and the heteroscedastic case, I've already shown you for the homoscedastic case, if you know the order, it will work. But for the heteroscedastic case, unfortunately, even if you know the order, as you can see from the estimates and their standard errors, there are biases in the estimates. Again, this is just reiterating a point that I made earlier. Let me close my talk with a second case study because all the time we cannot be talking of linear systems only. So the question that kind of bothers us is what happens if I apply this DIPCA to a kind of a closer to real system. So we took a two-tank system, agreed that it doesn't have very severe nonlinearities, but it has at least some nonlinearity. And the nonlinearity comes from the valve. There's a square root nonlinearity. The governing equations are given, the parameters are given here. We simulate the system. And since we are concerned or focusing on single input, single output systems, we pick the output as the liquid level in the second tank and the input as the inlet to the first tank. I don't have to tell you from the physics what is the order, right? Yeah, I leave it to you to figure out what should be the true order. Let us see if DIPCA actually discovers it. So we choose a stacking lag of L equals 4. Yeah, we could have chosen 15 or whatever, doesn't matter. So the converged guess of constraints turns out to be 3. And therefore, you can straight away calculate eta to be 2. And just for your own confirmation, yes, so here are the 3 close to unity eigenvalues. Again, yes, you may have to do a hypothesis test here to confirm indeed that the deviation from unity is 0. Here, insignificant. So this eta being 2 should be physically meaningful. And I think if you go back to the physics of it, yes, the relationship between H2 and the inlet flow rate is indeed second order, because each tank is a first order, has first order dynamics, or each liquid level in each tank has first order dynamics. So the estimated model is reported here, and the true model, the true one is a continuous nonlinear system. So we linearize and do a ZOH discretization at a sampling interval of 1 second, because that is the sampling interval that we use for collecting or generating data, is given here, and you can see the estimates are very close, right? So you can see that what we have essentially done is we have estimated the process order, the coefficients, and so on, despite the fact that there is a mild nonlinearity there. Now, whether this will work all the time, it's a $1 trillion question, because linear models estimated using PCA, when they are applied to nonlinear systems, there is hardly any discussion on this topic in the literature. It would be great to take this up as a research problem, and it will require at least, I would say, about 10 PhDs probably, or 5 PhDs to answer that question. There is kernel PCA and so on, but the question perhaps that would be of interest to ask is, what would PCA converge to? For example, does it converge to a linearized model within the vicinity of the operating condition? Can we prove that theoretically? And if yes, then what would be the stipulating or the binding conditions for such a result to be true? So we do not know at the moment. So just to summarize now, essentially DIPCA can automatically estimate model order, parameters, and noise variances of an LTI dynamical system. And in fact, what is not what I would like to draw your attention to is that we have a generalized method to handle both the classical and the EIV case. That means if I do not know which variables have errors and which are known with errors, are known without errors, we can still figure that out and do an identification. We don't need separate methods. Today you have a separate method for classical identification where inputs are known accurately, and EIV for handling the erroneous inputs. Here we are saying there is a generalized method, and we presented this paper at ICC, interesting. And I think, I'm not so sure if it was awarded the best paper, I don't remember. But yes, so there is a generalized method that is available. And as I said, we have now a MATLAB-based GUI version 1.0 that implements all the methods that we have talked about, the IPCA, DIPCA, and the hypothesis testing. And in fact, residual generation, I've not talked about residual generation. Shankar will talk about it tomorrow when he talks of state space identification. So that's it for today. We'll be very happy to take questions.
Yes, the audience can ask questions here directly, which is a bit different from the regular sessions. Here, anyone can unmute and ask a question directly. Please go ahead.
Can I go ahead?
Yes, please, Sanjay.
Yeah, okay. Yeah, I was just curious. So, you mentioned identification 101, but there's also time series 101, which uses similar. I mean, I remember opening the book and starting with like these kind of ARMA models.
Which
So-
book are you referring to?
I don't remember now. It was many years ago, but I guess there are many of them.
But hopefully, you will refer to my book on SysID.
So that's the big one, right?
Yes.
I have to
Yes,
get my
as
hands
Shankar
on
calls it, omnibus.
I have to get my hands on it someday. Yeah, so I was asking, I mean, they do these things like, look at some autocorrelation or something and identify the lag, and they have like a list of steps to follow.
Right.
So what bearing this has on that?
No, this is order the deterministic dynamical system. Okay. So it's a very good question, excellent question. In fact, at some point, I also thought that we could use this there. But the problem is that here we are looking at the underlying system is deterministic. Whereas if you were to, in fact, excellent question. Let me actually recollect my idea. So if you take, for example, as simple as an AR1 model. Okay, so I'm going to use a different symbol so that you don't confuse. So let's take an AR1 model and let's assume the signal that you're looking as VK. Then VK plus, let's say, D1 VK minus 1 is EK. This is the standard autoregressive model of first order. Suppose I want to identify the order of, and given that it is AR process, and I want to get a good estimate, an accurate estimate of P. Of course, theoretically, you have PACF. The partial autocorrelation function is theoretically known to get you the correct order P. So that is there. So PACF exists. Interestingly, PACF also has the terms PCA in a jumbled way. But that can get you. But suppose I want to use PCA on this. Unfortunately, I cannot, because it's not a deterministic relation. I do not know EK, right? If you give me EK, I can get it from PCA. But now you can turn to Euler-Walker equations, which says that the same governing equation is satisfied by the respective autocovariances. That is what essentially the Euler-Walker equation says for L greater than 0. So J equals 1 to B. You can use this if you know the autocovariances exactly. But again, what you will do is you can use PCA on the estimated autocovariances. You can use that provided the errors in the, so you can construct a stacked vector or matrix of estimated autocovariances at different lags. But the errors in the estimates have to be of, number one, they have to be Gaussian distributed. Okay. Maybe there is there is a result by Bartlett which says asymptotically errors in ACF estimates are Gaussian distributed. But then there may be heteroscedastic, and you can use IPCA in that case. So there is a remote possibility of using IPCA on this, where you stack up to a large lag, the estimated autocovariances up to a large lag, and then basically run IPCA on it and maybe get an estimate of P. We have not tried, but that was the thought process up to which I stopped in applying IPCA to time series models. But it's an excellent question. Yes.
But you anyway you can accommodate noise in your input. So can't I treat this as an input 0 with some noise?
Yeah, but you don't know EK, right? EK is fictitious, it's endogenous, it's a part of EK. EK is not some exogenous one. It's endogenous. It's a part of EK.
Oh, it's not just noise, is it? Okay.
It's a part of BK. So it's an unpredictable, or the irreducible uncertainty of BK.
Okay. All right. So a bunch of other questions, but unfortunately I have to go to the other session which I'm supposed to chair. So maybe after tomorrow's session,
yes.
we won't have any constraints. I could ask them at that.
Oh yes, no constraints. Correct. That's a good word to use.
Okay. Okay.
Right. Sure. Thanks. Thanks a lot.
Thanks.
Nice
Thanks.
session. Any other question? Okay, so it looks like I don't see any typed questions or audio questions, so maybe we can wrap up the session.
Yeah, looks like there are no more questions.
Sure.
Okay, in that case, thank you, Professor Tangirala, once again. So,
Yeah, thanks a lot. Thank you for hosting this and giving us this opportunity. And tomorrow's both sessions will be handled by Shankar. Of course, I'll be there. He'll be the main speaker.
right. So tomorrow, once again, we have the fifth and the sixth and final sessions of this tutorial. Same time. I think the first one is at 11:30, if I'm not mistaken.
Yeah, and 5 o'clock. Yeah,
And
same time.
yeah, and the next one, the sixth one, will be at 5 o'clock.
Yeah, easy to remember. Same time.
Okay, everyone.
Yeah, thank you.
Yeah, thank you. Bye bye. Take care.
Bye.
Bye.
So I'll end this session then. Thank you.
Yeah, please. Yeah. Thank you.